Energy band structure of silicon. As you know, all group 4A elements in periodic tables are having completely filled S bands and partially filled P bands. All group 4A elements in periodic table has completely filled S bands and partially filled P bands. Silicon also, we are considering silicon. Silicon is group 4A element. In periodic table. Its atomic number is 14. Atomic number is 40. And so its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p2. So as you can see that in this case, in the case of the silicon, 3s is completely filled, but 3p is partially filled. Now here we are going to consider atom. Consider isolated atom. That is when atoms are separated by distance infinity. Let's see its electron energy levels. So this is 1s energy level which has 2 electrons. This is 2s energy level which has 2 electrons, and this is 2p energy level which is having 6 electrons in silicon. Then there is a 3s here which is completely filled, that is it has 2 electrons, and then this is the 3p energy level. It is a partially filled. Instead of 6 electrons there are only 2 electrons available. So this is the energy level diagram for the isolated atom. On the y-axis there is the energy, x-axis there is the interatomic distance. So when the solid is formed, consider a solid of, now in a solid of n atoms. We are considering solid which is having n number of atoms. So initially when atoms are separated, they have this discrete energy levels. When atoms are brought together, since 2p is the outermost orbit here, not 2p, 3p is outermost orbit. So the 3p energy levels first start interacting and then their splitting will start. So first initially 3p splits and then 3s splits. So as you can see here, 3p splitted here and 3s also splitted. So let us consider this 3s and 3p. First 3p splits This 3p will be having 3n energy levels. It is having 3n energy levels and therefore 6n quantum states. And its capacity is it can accommodate maximum 6n electrons. 6n electrons is the capacity. When it's splitted, 6n maximum electrons can be accommodated in it. However, only 2n are available. Only 2n electrons are available. So this 3p is partially filled. So it starts splitting here and this one is partially filled. After 3p, 3s starts splitting. And when it splits, the 3s band will be having n energy levels. 2n quantum states. And its capacity to accommodate electrons is 2n electrons. Is capacity. However, this band is completely filled. 2n electrons are available here. 2n electrons are available. And hence this band is completely filled. And this 3p band is partially filled. Let's see the diagram. So in this diagram, when they split, when 3p and 3s splits, 3p is partially filled and then 3s is completely filled. As we decrease interatomic distance further, these two bands, 3p and 3s, merge into each other and form a composite band. As interatomic distance decreases further, this 3s and 3p bands overlap and form a composite band, or you can say hybrid band. In the diagram, as you can see here, as interatomic distance further decreases, these two bands over here and here, they merge into each other and form a hybrid band. Here is hybrid or composite band is formed. As we decrease interatomic distance further, then this hybrid band divided into two equal bands. It splits into two equal bands. Let me write that. As interatomic distance decrease further, hybrid band splits into two equal bands. Let us call it lower and upper band. So in the diagram, this is upper band. As you can see, it divided into two equal bands, and let's say this is the lower band. So this hybrid band or composite band, as you can see in the diagram, it splits into two equal bands, and as further interatomic distance decreases, the splitting will increase. And you see this diagram, on the x-axis there is interatomic distance, y-axis is energy axis. And in this case, A naught is actual interatomic distance. So at actual interatomic distance, you can see here these 3p and 3s bands. Initially they merge, they form the hybrid band, and then they split into two equal bands. However, this 2p, 2s, and 1s are not splitting at all at actual interatomic distance. So let us find out now here in the hybrid band, how many energy levels are there? Consider hybrid band here. In the hybrid band is a composite band of 3p and 3s. 3s band is having n energy level, 3p is having 3n energy level. So in hybrid band, there are 4n energy levels. 4n energy levels, and therefore 8n quantum states. Its capacity is 8n electrons. It can accommodate maximum 8n electrons, that is its capacity. But how many are available electrons? As you can see here, this is completely filled, 3s, but 3p is partially filled. In 3p, there are 3n energy levels, and in 3s, there are n energy levels. So here in the hybrid band, there are 4n energy levels over here. Then in 3p, there are 6n quantum states. In 3s, there are 2n quantum states. So 6n plus 2n, 8 quantum states. And its capacity is 8n electrons. But here, available electrons in 3p are 2n. Available electrons in 3s band is 2n. So even though the capacity of hybrid band to accommodate electrons is 8n, but only 4n electrons are available. Hence, you can say that this hybrid band is half filled. We have half filled hybrid band. Then in the diagram, as you can see, this hybrid band splits into two equal bands, upper band and lower band. So at actual interatomic distance, here A naught is actual interatomic distance. At actual interatomic distance, this 1s, 2s, 2p are not splitting at all, Only you can see here there are two bands, one is upper band, another one is lower band. So let us write what is in the lower band and what is in upper band. In lower band, as I said, they are splitting equally. In the hybrid band, there are total 4n energy levels, and then it splits into two equal bands. So this lower band will be having 2n energy levels, and this upper band is also having 2n energy levels. 2n energy levels means 4n quantum states, and 4n electrons is capacity. Maximum it can accommodate 4n electron. Similarly, in upper band also there are 4n energy quantum states, and its capacity is 4n electrons. However, in the hybrid band, available electrons are only 4n. It has capacity 18 electrons, but only available 4n electrons. So all these 4n electrons will occupy the lower band, because the electrons first fill the lowest energy levels. So all these 4n electrons will go in the lower band. So in the lower band there are 4n electrons. So this lower band is completely filled. But in the upper band, all 4n electrons are gone and occupy the lower band. So in this case, 0 electrons available. So this upper band is completely vacant. See the diagram. Hybrid band splits into two equal bands. Now the lower band is completely filled, upper band is completely vacant. And at A naught, we are going to slice it to get the energy band structure. And as you can see here, they are sliced. And here we got the two bands. This one is upper band, which we are calling conduction band. And this one is lower band, we are calling it valence band. So this is nothing but upper and lower. This lower band is valence band. So valence band is completely filled at absolute zero temperature. Upper band is called the conduction band, and this conduction band is completely vacant at lowest temperature. Then in this case, this is the gap between these two bands. That is this gap. So this gap is band gap, which is denoted by Eg. So here is Eg. And in the band structure, there is no need to show the lines, but these are the lines for this 1s, 2s, and 2p, because they are not splitting at all. So this is the band structure of the silicon, and you know the band gap of the silicon is 1.1. So if you supply the thermal energy, the electrons in the valence band absorb that thermal energy, and if that thermal energy is more than the energy gap, then electrons are excited into the conduction band, which produce holes in the valence band and electrons in the conduction band. Both are the charge carriers, and the current can flow through it.